Alright guys, here's the thin film interference problem. So you gotta, again, you'll have some coating on top of a substance. So it could be oil on water. In this case, you got a camera lens where it's trying to minimize reflected light. So it's like a glare coating. Well, it's a coating to prevent glare, if I could talk. So I got a picture here. So you're always you got your three surfaces. The thin film will be in the middle. Camera lens with an index of refraction. So the actual lens is 1.5. So that's our n value. So n3 is 1.5. The index of refraction is the variable n. Again, these variables are out on the notes. The index of refraction doesn't have units. It's just a number that describes the medium. And then it's coated with a thin film of magnesium fluoride, 1.24. So that's N2, 1.24. Here, we'll kind of keep these separated. And if it doesn't give us the other one, but you can make a reasonable assumption. That's air, which is around 1. It's close enough to 1. What should be the least thickness? So what the least thickness of this film, we're looking for T. With a wavelength of 450 nanometers. So they're looking to, what is the least thickness of the film? To minimize reflected light. So they just want to minimize this 450 nanometers. So that's lambda. All right, the first thing you want to do is the lambda we need is actually the lambda in the film. So we need to take a second, and we'll do that right here. But the lambda incident, so the actual one coming in, we want, lambda medium is what we want. Lambda medium is going to be the incident wavelength, that 450, divided by the index of the medium. So in this case, it's going to be 450 nanometers. And we can leave everything in nanometers, it'll work out. Divided by 1.24. So what do we got there? 450 divided by 1.24. So 363, I'm rounding a little bit, 363 nanometers. So that's the wavelength we want to use to determine if it's, what does it want? The thickness. So here, I gave you some pointers. You want to start with, so besides that, we do need remember to use the wavelength. So I started with my third pointer first. But here, back to the pointer. Start problem based on constructive or destructive. Well, they want to minimize the reflected light. So that's telling us that they want it to be destructive. Well, let's start at the beginning. So delta L is going to equal destructive. Remember, it has to be off by half a wavelength. So we're going to have add that 1/2 to the M value to shift our waves. Delta L for a thin film, you have to go through the film, so here, and then back out through the film. So that's twice the thickness. You have to go through the film twice. So you have 2T. Delta L is really 2T. So here, this is the generic equation we're starting with. Then we're going to rewrite it in terms of what we actually have. We need to look at, well, what happens to the wave? If the wave didn't do anything, this would be our equation. If it didn't flip. So remember, when the wave hits the top surface, it could invert itself. When it hits the bottom surface, it could invert itself. We have to do our little checks with the indexes. But let's say there is no change, then this would be the equation, and we want destructive. But to know if there's change or not, we got to look at these indexes. So from N1 to N2, so we do the two surfaces. We do the top of the film, and we do the bottom of the film. We're going to compare those. So going from air to the film, that's a low to a high. So this is low to high. Remember, the change is pi. So that our wave's going to shift when it reflects off that surface. This other substance, this is also, so now we're going from 1.24, which is a low, to a high. We're going to have another phase shift. So both those waves are going to phase shift on us. So that cancels out. They cancel out, and we are good to go with m plus 1/2 times lambda. If this had been, say this was a low to a high, but then say this N3 was air again, then N3 would be 1. Then we're going from a high to a low, change is no. High to low, change is no. Which would mean we have one phase shift. So that would take this equation. So we do have a naturally occurring phase shift just from the wave reflecting off the surfaces. So we would change this to m lambda. It would get rid of the 1/2, since it's going to invert itself. So we don't need to include that in the equation, since the wave's going to do it itself. So you would just drop that 1/2 off. So 2t, 2 times t. So what is m? Well, it said minimum, and that's usually what they want. So minimum here would be when m is 0. So we would end up with 1/2 lambda. So we got 2t equals 1/2, and we know lambda is 363. Remember, it's the lambda in the medium. So our thickness is going to be 363 divided by 2, and then divided by 2 again. So there's your 91 nanometers. So minimum thickness at 91 nanometers would be your minimum. Double it, you'll get another one. Triple it, you'll get another one. So you could make thicker films that could also do the same thing. But this again was the minimum film thickness.